Okay, the derivative of a function. We've now arrived at a crucial point in the study of calculus. The limit used to define the slope of a tangent line is also used to define one of two fundamental operations of calculus: differentiation. So the definition of the derivative of a function. The derivative of a function f at a given point x is given by, here's some new notation here, f prime of x. We have this little like apostrophe up here. F prime of x is the same as the limit as delta x approaches 0 of this difference quotient. You know, our f of x plus delta x minus f of x over delta of x, provided that this limit exists. For all x for which this limit does exist, f prime is a function of x. Be sure you see that the derivative of a function of x is also another function of x. This new function gives us the slope of the tangent line to the graph at any given point, provided that the graph can have a tangent line at this point. The process of finding the derivative of a function is called differentiation. A function is differentiable at x if its derivative exists there, and is differentiable on an interval from a to b if it's differentiable at every point in that interval. In addition to the prime notation f prime of x, which is read as f prime of x, other notations are used to denote the derivative of a function y equals f of x. The most common are f prime of x we've just talked about, or here you see dy over dx, or the derivative of the function y. You know, here we're using y to stand for the function. Dy dx, the derivative of y with respect to the x variable. Or we could even just simply put a prime above the y prime. Or d dx, the derivative with respect to x of f of x. This one I've hardly ever seen used at all. You know, so let's not even worry about that one. These are the biggies: f prime of x, or y prime, or dy dx. You know, this one we won't even use too much in this class. Again, some reading below. The notation dy over dx is read as the derivative of y with respect to x, or simply dy dx. Using limit notation, we can write it this way: dy dx equals the limit as delta x approaches 0 of delta y over delta x. And this delta y over delta x, you know, with our prime notation is here, the limit as delta x approaches 0 of our difference quotient. And that's the same as f prime of x. Alright, let's do, we did a parabola one in the last video. We had x squared plus 1, and we used this limit definition to find the derivative. Let's do one a little harder. X to the third plus 2x. So we want to find the derivative. We want to find f prime of x, and that is going to be the limit as delta x approaches 0 of our difference quotient. So let's get ready. There's going to be a lot of just algebra work going on in this problem. So we want the limit as delta x approaches 0, and we're going to have our difference quotient. Well, let's look at our function up here. X to the third plus 2x. So something to the third plus 2 times something. We're going to have something in parentheses to the third plus 2 times something. And then we're going to subtract that same function again. Bracket this off. So we're going to have something to the third plus 2 times something, all over delta x. Now when we start plugging our things into the parentheses here, remember first we're going to have x plus delta x. So here we're going to have x plus delta x quantity to the third power plus 2 times x plus delta x. And then in the second time we wrote out the function, we just plug the original back in, x to the third plus 2x. So x to the third plus 2x. Alright, so we have the idea from calculus. We're going to set up this difference quotient, let our limit as delta x approaches 0 to find that derivative, but we're going to have to do a lot of little Algebra 1 scratch work here. So the first thing is going to be to FOIL out this quantity, x plus delta x quantity to the third. Now we could, do FOIL on it once and get that answer and then FOIL it again. Or if we remember binomial theorem, I think that is listed somewhere in the back cover of your calculus textbook. If we start to FOIL this out, remember there's a little trick to it. A binomial to the third power, well, our first term is going to be this first x to the third power, x to the third. And then we're going to have, since this is plus, we're going to have plus 3 times the first term squared. So x, we're going to square it, times the second term, delta x to the first power, plus another coefficient of 3. Now, the x drops down to the first power, and the delta x is squared. Delta x quantity squared. And then we do plus the last term to the third power, plus delta x to the third. Ooh, I might be running out of room here a little bit. Still got some, actually, let me just shrink this up. We'll be able to squeeze it in. Like that. Just a little bit smaller. Okay, now we've done the binomial to the third power. Now we just got to distribute this 2. 2 times x is plus 2x. 2 times delta x becomes plus 2 delta x. Extend my line. So we got the first part done here. Now it's easy, we're just going to distribute the negative. This x to the third becomes minus x to the third. This 2x becomes minus 2x. And that's all over delta x. Okay, let's see what cancels. Leading term, x to the third, and we have a minus x to the third. Those disappear. Next term has a delta x squared, delta x. Ooh, here we have a 2x. This is plus 2x, and this is a minus 2x. So those cancel. So let's see now. Every term remaining in the numerator has a delta x in it. Let's collect them up. Not red. There we go. The limit as delta x approaches 0. In the numerator, now we have a 3x squared times delta x plus 3x times delta x squared plus delta x to the third plus 2 delta x, that's an ugly delta, delta x, that's it, and it's all over delta x. And the key here again is the denominator is delta x. We need every term in the numerator to have a delta x to cancel out. And we do have that here. So let's see. This delta x on the denominator is gone. This is delta x to the first power, so that's completely wiped out. This delta x squared gets knocked down to delta x to the first power, so I'll scribble out the squared. This delta x to the third becomes delta x squared, so that got knocked down. Here we have 2 times delta x. This delta x is completely gone. And now I like to say we apply the limit. We let delta x go to 0. So every delta x now becomes a 0. Well, here that delta x is gone, so we now just have a 3x squared for this term. Here we have 3x times delta x. Well, this delta x is now 0. 3x times 0 is 0, gone. Here we have delta x squared. Well, delta x is now 0. 0 squared is 0. And this delta x is also gone, and we're just left with a 2, so we keep that 2. 3x squared plus 2. So there's our derivative, f prime of x. F prime of x. Now, I want to say it again. I think I slid it off over here. Remember, the derivative of a function is also a function, and it's used to find the slope of the tangent line at any point on the graph. So, well, this isn't going to be real precise, but here's an xy axis. Our original function, x to the third plus 2x. The x to the third tells me it's going to open up to the right, down to the left. The plus 2x is going to move everything up steeper, faster. So this graph roughly is going to look like this. So here in blue is our function. And I should have switched colors. Let me change this to red. So our original function, x to the third plus 2x, looks probably roughly something like this. We manipulated this. We played around with it with our quotient, our quotient there, and found the derivative of this function. And that function is 3x squared plus 2. Now, what exactly does this mean? Here is x is 1. If I plug in 1 into the original function, I'm going to get 1 to the third plus 2 times 1, and that turns out to be 1 plus 2 or 3. So if I plug in a 1, at the height over here, it is a height of 3. So this point 1, 3 is on the graph. Well, what is the slope at that point? What is the slope occurring right there? What would the tangent line slope be? Well, we have this derivative. If I take this same x value of 1 and I plug it in here, 3 times 1 squared plus 2 is 5. So I know the height at this point is 3, and I know the slope occurring here is 5. M equals 5. If I drew a tangent line, it would be positively sloped, and it would be pretty steep. Okay, so the derivative of a function is also a function. We plug x values. Oops. What did I just do there? Oh, there it is. We plug x values into the original function to find out our height on the y-axis, to find our location in the xy coordinate plane. If I want to know the slope occurring at any given x value, I plug that x value into the derivative function, f prime of x. Okay, example 4. Using the derivative to find the slope at a point, find f prime of x for this function, the square root of x. Then find the slope of the graph of f at these points, 1, 1, and 4, 2. Discuss the behavior of the function at the origin, 0, 0. Okay, this is going to be a little different than what we did before. Here we're going to need to fall back on an old algebraic trick of conjugates, and you'll see what I mean here in a little bit. So we want to plug our function in. Here our function is x, or the square root of x. So to find our derivative, f prime of x, let's see here first. Our function is f of x plus delta x. So we're going to have these, or our function is just square rooting something. Square root of something minus the square root of something over delta x. Well, first goes in our x plus delta x, the square root of x plus delta x, minus the square root of x. And that's, again, all divided by delta x. And, ooh, where are my manners? I forgot my limit notation, because we always got to remember this is the limit as our delta x approaches 0. That is f prime of x equals. You know, it'd be nice if we could just, plug in 0 for delta x and not have divide by 0 and get it over with that way. But we can't do that. We're going to have to play around with this a little bit algebraically. And I'm going to need a little room here, because I did give you a hint. We are going to need to use a conjugate from algebra. We are going to take this that we can't do anything with right now, and we're going to multiply the numerator and denominator by something else that will hopefully simplify and clean this up a little bit. Well, what is our conjugate going to be? In our numerator here, we have a square root minus another square root. Well, if we come up with a conjugate that we can FOIL that out and get those square roots to disappear, that's going to help move us along. So here we have a radical minus a radical. Well, our conjugate is going to be the same radical plus radical. So we're in the first one, we're going to have our x plus delta x, and in the second one, we're going to have just our plain old x. And if we multiply the numerator by this conjugate, it's only fair that we multiply the denominator by that exact same conjugate. That way, anything divided by itself is 1. We're sort of multiplying this limit here by a form of 1. Okay, the calculus is there, the concept is there. Now again, we got to fall back to some old algebra skills. So we have here a binomial times a binomial, and it is a sum and a difference. So if I multiply first term times first term, and let me not forget my limit notation this time, the limit as delta x approaches 0. So here we have a radical times another radical, and those radicals are the same, x plus delta x. So that times itself is just going to be, the radicals disappeared. It's a square root times a square root. That becomes a square root quantity squared, and the radical disappears. So our first term is just going to be x plus delta x. If we look at our outers and our inners, when we FOIL, here we're going to have a radical times the root of x, and then on the inside we're going to have the negative square root of x times that bigger radical. So those inners and outers, when we FOIL, will always cancel. That's why we choose the conjugate. They're exactly the same except in sign. This is a plus, this is a minus, so it becomes our first term quantity squared, so our radical disappears, minus our second terms squared. Square root of x times the square root of x is x. Now in the denominator, we could distribute. We could have delta x times the first radical plus delta x times the second radical. Let's not distribute that. So here we're going to have our delta x times this, and I'm just going to leave that in parentheses. Our conjugate of the square root of x plus delta x plus square root of x. Oops, and I put my closed parentheses in the wrong spot. That should be over here. So I just multiplied this denominator times the conjugate, but did not distribute. And you're going to see why in just a second. Let's just look at this numerator up here. Combining like terms, we have an x and a minus x. Well, x minus x is 0, so these go away. Gone. Now, our numerator is simply delta x. Down here in the denominator is another delta x we can cancel it with. And I'm just going to rewrite this to show you a common mistake I've seen over the last few years. Up top, we have a delta x. Down in the denominator, delta x times that conjugate, x plus delta x under the radical plus square root x. I see, so many times students just want to do this. They want to cancel and then just have the limit as delta x approaches 0 of this in the parentheses. Don't forget this delta x up here in the numerator. There is a coefficient there. There's a 1, an implied 1. So when these cancel out, there's still that 1 in the numerator. Oops, that was supposed to be an eraser. There we go. So remember that conjugate in those parentheses, that's in the denominator, and it stays as a denominator. So we're going to have the limit as delta x approaches 0. Because this delta x canceled doesn't mean there's nothing left in its place. There is a 1 up there. 1 over the square root of x plus delta x plus the square root of x. Now we can apply that limit without a divide by 0 scenario. So as we let delta x go to 0, this delta x just sort of falls off. It goes away. So we've applied the limit. We can drop the limit notation. Now we have 1 over, well, when that delta x there went to 0, we're going to have the square root of x plus the square root of x. What is the square root of x plus the square root of x? Well, that's 1 over 2 square roots of x. There is our derivative, our f prime of x. F prime of x. We set up our limit, we simplified, we applied the limit, we let delta x go to 0, and this is what we were left with. 1 over 2 times the square root of x. And again, I cannot hammer this home enough. Down here in the type, oops, there we go. Remember, the derivative of a function is a function. This function can be used to find the slope of the tangent line at any given point. Again, here, the square root of x, we could graph that. We could plug in, say, 4. The square root of 4 is 2. That is our position function. That is our height or our placement in the Cartesian plane. We plug in a 4, we square root it, and get an output value of 2. So we know the point, 4, 2, is on the graph of square root of x. What is the derivative at this point? Well, we'd plug this x value of 4 in here. The square root of 4 is 2. 2 times 2 is 4. The derivative there, the slope at this point would be 1/4. M would equal 1/4. And it looks like I do have the graph down here. Let's take a peek at it. Aha. Yeah. So we plug in the 0.4 into the original function. We square root that and get an output value of 2 on the y-axis. So there's our 0.42. That is our position in the Cartesian plane. At this point, what is the slope? Well, we had our slope function. Our derivative was 1 over 2 roots of x. We plug this same x value of 4 in here and get 1/4. That would be our slope at that point. And let's see, I think we'll do one more on this video, example 5. In many applications, it's convenient to use a variable other than x as the independent variable. Here we're going to use t's instead of x's. This, when I took Calc 2 in college, this was a bit of a problem. They throw so many different notation, just variables at you. It's real hard to get, confused and lost in the shuffle. I did for a while in college. Whenever they gave me anything other than an x variable, I changed everything to x's, and then I did the problem. And then when I got my answer, I converted back to the variable, that was originally given in the problem. But we are going to do this with respect to t. Find the derivative with respect to t for the function y equals 2 divided by t. So now instead of, in the last one we did a weird function, that was the square root function. Now we have 2 over t. So we want to find this derivative. We want to take, and our function was given as y equals 2t. Well, we can write, that derivative as dy, the derivative of the function y, and what variable are we using with respect to t, dt, dy dt. So that derivative is going to be equal to the limit as when delta t approaches 0 of t plus delta t, that function, minus f of t all over delta t. So let's see here. The limit when delta t approaches 0 of, well, we're going to take our function, we're going to have 2 over something minus 2 over something all divided by delta t. Delta t. And what goes in those parentheses? Well, in the first one, it's going to be t plus delta t. And then in the second one, minus just the original function, 2 over t. So we want the limit as delta t go to 0. We can't make that equal to 0 now, or we get divide by 0. So we're going to have to do something algebraically to that numerator to hopefully get something to simplify. And the only thing I can see right now is we are subtracting 2 fractions. So let's try to get a common denominator, subtract the fractions, and see what happens from there. Okay, the limit when delta t approaches 0. Here's our big divider line. Down in the denominator is just our delta t. So we have 2 fractions up top, 2 over this denominator minus 2 over a different denominator. Well, that common denominator, if you remember a little pre-calc from last year, is going to be these 2 denominators multiplied together. So we're going to have t times the quantity, t plus delta t. And we have to fix up our numerators. Well, this denominator, we were missing this piece over here. So we're sort of going to, remember I talked about this last year, it's sort of like cross-multiplying. Here we're going to have 2 times t. So up top here, 2 times t minus, and then we're going to sort of cross-multiply the other way. This denominator had the t. We were missing this t plus delta t quantity, so we're going to multiply this numerator by what it was missing in the denominator. And remember, because this is a minus, we do want to bracket this off. Very easy to forget and not distribute that negative. So when we multiply this way, we're going to have 2 times that quantity, t plus delta t, and parentheses. Okay. And now we just, fall back on our algebra skills and simplify as much as possible. Hopefully, we'll get an opportunity to cancel with that delta t in the denominator. So, oops. And I don't want to forget my limit notation. notation, the limit as delta t approaches 0. Well, we're going to distribute this negative, and well, I guess we could say first we should distribute that 2. Here we're going to have 2t plus 2 delta t. When I distribute this to 2t, 2 delta t, and then we distribute the minus sign. So here we have up front, first is our 2t, and then we're going to distribute the minus 2t, and then distribute that negative to the second term, minus 2 delta t, all over this denominator, t times t plus delta t. And let me change back over to red so this stands out, all over our final denominator, delta t. So our upper part of the fraction, the overall fraction, the numerator within the numerator, looks like some stuff is going to cancel here. We have 2t minus 2t, that goes away. So now we have the limit as delta t approaches 0. So up top here, oh, and let's even look at it this way. In this denominator in red, we have, the divider line. Up top here, we have a numerator and denominator. Down here, we could think about this as a numerator over 1. And I'm going to bring this up and flip it. Remember, this is a fraction, this upper fraction, divided by a lower fraction. When we divide a fraction by a fraction, we invert and multiply. So first, let's look at the upper fraction here. We have a minus 2 times delta t over this denominator, t times the quantity, t plus delta t, t plus delta t. And I'm going to bring this one up and flip it, invert and multiply. So down here it's delta t over 1. I'm going to bring it up, and this is now going to become times 1 over delta t. And you can probably see the reason I did that. Here on the diagonal, we're multiplying two fractions, so we can cancel these on the diagonal. They divide each other out, and we sort of just replace them with a 1. So those sort of go away. So let's rewrite this a little cleaned up here, and then we'll apply that limit. We'll let delta t go to 0 and see what we're left with. Okay, so in just a minute we are going to apply that limit, but I'll write it one more time. The limit as delta t goes to 0. Up top, and when we multiply, this is basically now a 1, so this is gone. We have negative 2 over t times the quantity, t plus delta t. The delta t is still in the denominator, but it's not alone. There's some other stuff down there. So as we apply the limit, let delta t go to 0. This becomes a 0. T plus 0 is just t. So now down here we have t times t. And t times t is t squared. So we get minus 2 over t squared. There is our derivative. And remember, the derivative of a function is a function. And let me rewrite it down here. What did we have? Y. So our original function was y equals 2 over t. And then our derivative, dy dt, the derivative of the function with respect to the t variable, is negative 2 over t squared. If I plug a t value in here, I get its position on the Cartesian plane somewhere in the xy axis. If I plug that same t value into the derivative function, I get the slope that is occurring at that point. The derivative of a function is itself a function. Alrighty, that's a good spot to end this video. There should be one more where we talk about differentiability and continuity.